All right, I want to talk a little bit about atomic mass and how it relates to the periodic table, to moles, and then to individual number of atoms. Because as a chemist, of course, we care about teeny tiny little particles, and the mass of the individual particles is going to make up the overall macro level mass of whatever sample that we're looking at. So we've learned that on the periodic table, this number on the bottom is the atomic mass, and this is a weighted average of all of the isotopes of that particular element in the universe, right? So we've defined atomic mass before as the mass of one atom of an element in atomic mass units, or just U is the international standard unit, which is based around the mass of a proton or a neutron. But the atomic mass, now that we've learned about the concept of moles, so let's remind ourselves about moles. 1 mole is equal to 6.02 times 10 to the 23rd of whatever it is that we're talking about. Particles, basketballs, donuts. So let's go with atoms for right now. But it could be 1 mole of atoms is equal to 6.02 times 10 to the 23rd atoms. 1 mole of lasagna is 6.02 times 10 to the 23rd lasagnas, right? So from there, this is the concept of a mole, and this atomic mass on the periodic table is also incredibly important because it is also the molar mass, which is the mass of 1 mole of this element. And the units on that are in grams. And grams are a much more useful unit to chemists because we have balances in our lab that are calibrated to take the mass of things in grams, or our SI unit for mass is in kilograms. So that's a much easier unit to work around than something like, well, first of all, atomic mass units. No one has a scale in AMU. And in terms of individual atoms or in terms of individual moles, we want to know how much we can actually measure out in the lab. We're experimental scientists, so the molar mass is important. So the atomic mass and the molar mass are both the same thing on the periodic table. It's the mass, the weighted average of 1 atom, but it's also the mass of 1 mole of atoms. So if I'm thinking about my carbon here, then 1 mole of carbon is 6.02 times 10 to the 23rd atoms of carbon, which is equal to 12.01 grams. Okay, kind of wacky, because if you picture 12.01 grams, that's not that much. If you measure it out on a balance, then that is not that large of a mass, and it has 6.02 times 10 to the 23rd atoms of carbon in it. Very cool, much more useful. Now, because we have this relationship between moles to atoms and atoms to grams and grams to moles, these are all interconnected, then we can use this information as a conversion factor. So let's practice with this idea. Let's take a compound that has carbon in it. Let's take calcium carbonate. Calcium carbonate. So carbonate CO3 with a -2 charge is one of the polyatomic ions that's pretty common, and calcium with its +2 charge, together they form an ionic compound, calcium carbonate. So in order to find the molar mass, so if I wanted to say, what is the molar mass? So maybe that's going to be useful for some reason. We'll get into the some reasons when we talk stoichiometry in a bit. Then I would go to the periodic table and I'd find calcium. Calcium is 40.08. And then I'd go and I'd find my carbon, which we already know is 12.01. And then our oxygen, which is 16. Now calcium, I just have 1, right? The subscripts here tell me how many of each of them there are in this particular compound, so it's a 1:1:3 ratio. So that would be multiplied by 1, carbon by 1, my oxygen by 3. And when I add those 3 things together, so I'm going to add these together, take the sum, I end up with 100.09 grams per mole. grams per mole. And that's a 9 and that's a G, just to make sure that there's a distinction there. In terms of significant figures, because I was given hundredths places on my periodic table, then I'm going to retain a hundredths place when I add them together. Remember, for adding and subtracting in significant figures, we're looking for the least number of decimal places, which in this case is our hundredths, so that's what we're going to round to. So you'll see that we actually grew a significant figure when we started to add them all together. So what this means is that 1 mole of calcium carbonate is 100.09 grams. So if I have a bottle that is labeled calcium carbonate and I take and weigh out and I put it in my little weigh dish, 100.09 grams of it, then that will give me 1 mole, or 6.02 times 10 to the 23rd molecules of calcium carbonate. Okay, so 6.02 times 10 to the 23rd of that particular ionic compound, calcium carbonate. And again, this is useful information because I can go from molecules to grams, from grams to moles. I could even go from molecules of calcium carbonate to individual atoms that are within that particular compound. So once we have these relationships, then we can start to interchange them. So let's look at some examples of that. Let's go to the mass in grams of 1 mole, 1.52 moles of sodium chloride. So the first thing that I need in order to find grams is I know how many moles I have, so I need to know that molar mass again. So then I'm going to go back to the periodic table. So here's my compound. I'm looking at sodium chloride. Oops, let's make that a loopy kind of L. That's a chlorine, believe it or not. Okay, so my sodium is 22.99. That's coming from my alkali metal here. And then my sodium, or my chlorine is over here in my halogens. 35.45. And when I add those two together, I end up with 58.44 grams per 1 mole of sodium chloride. So that means that 1 mole, again, just for clarity, is 58.44 grams. Okay, I like to kind of unpack whenever I have stacked units like this, and we've seen this before with density as well. Whenever I have stacked units, I like to kind of take it apart and put it into its component pieces, because this helps me to remember that this is the ratio. Because once I have a ratio, 1 mole to this many grams, then it doesn't really matter which side of the fraction, which side of the numerator or the denominator of the fraction that these units are on, because I can put them on either side when it's an equality, and I can use that equality as a conversion factor. So let's do that. So we need to start with what we're given. That's our 1.52 moles of NaCl. And now we're going to go from moles of NaCl. We're setting up kind of our roadmap here to go from moles to grams, which is what we're asked for. What is the mass? Well, the mass is going to be in grams of NaCl. Okay, so then once I've put my units in there, my moles are going to divide out. I'll be left with grams of sodium chloride, and now I can plug in my numbers, right? For every 1 mole of sodium chloride, it's 58.44 grams, and now I can multiply across, and my calculator will tell me that it is 88.8288 grams. Well, it won't have the grams, but you know what I mean. So it's this many grams of sodium chloride. And if I was happy with that answer, which it's a nice answer, it's got a lot of symmetry to it. I like all the 8s in there, but it's got too many sig figs, right? We have to always think about significant figures. So the periodic table gives you a mass that is an average, right? It's a weighted average of all of the isotopes. So we do have to factor it in when we're thinking about significant figures. There are 4 there in the mass that I'm given. I'm only given 3 significant figures in our moles. So we're going to have to round our answer to 3 because we're doing multiplication and division here. So that means that I have 1, 2, 3 that are significant. I'm looking to the 2 to round, which will round down then because it's less than 5. So that's going to give me 88.8 grams. Few too many decimal points there. 88.8 grams of sodium chloride. All right. So that's pretty straightforward. That's kind of one step then to go from moles, if I know them, to grams, and that's going to be a useful skill. And again, I could have been given it the other way around. I could have been given grams and figured out how many moles there were. So let's look at another example which now looks at atoms. So we're going to an even smaller level, which is kind of a fun one. So how many atoms of phosphorus are there in 2.85 grams of phosphorus? So I take my container of phosphorus, I measure out 2.85 grams on my balance, and I want to know how many atoms are in that sample. Well, how cool is that? Well, what I need to know then is I need to go to my periodic table, and here's phosphorus. Chemical symbol is P, so phosphorus on the periodic table is 30.97. And so we just learned that the atomic mass is also the molar mass, so that's the number of grams per 1 mole, which means that 1 mole of phosphorus is 30.97 grams. Again, just for clarity. So I think it's important because this gives us an equality. It doesn't matter where on the unit, if it's on the top of the fraction, the bottom of the fraction, this just kind of disambiguates that a little bit. Okay, now we also, because it's asking for atoms specifically, we also know that in 1 mole of anything, there's 6.02 times 10 to the 23rd atoms of phosphorus. And these are all going to be important pieces of the puzzle when we start to put together our dimensional analysis, which is what we're doing. That's our skill. All right, we've got this. We can do this. So I have 2.85 grams of phosphorus. Now, I can't go directly from grams to atoms. Actually, I could. I could say for every 30 grams, I have this many atoms. But let's do it in 2 steps just for fun, because you could do it that way, and that's totally fine. Depends on your comfort level with dimensional analysis. It depends on your comfort level with your unit conversions. So I am going to do it the long way, because in my chemist's brain, this is what I think about it in. So here's my, my molar mass. So my grams on the bottom will divide out, and I'll be left with moles. And I know how many atoms are in 1 mole. It's 6.02 times 10 to the 23rd. And you'll note that I'm being pretty careful with my units here, and it's not just grams, it's grams of phosphorus. And it's not just moles, it's moles of phosphorus and atoms of phosphorus. It's going to be important to keep track of your grams and your moles and of what you're talking about there, because you're going to run into, when we get into more complicated problems where we're converting from moles of one thing to moles of another thing, that it's just going to be easier if you make sure you label your units specifically. Okay, so now we have 2.85 divided by this guy multiplied by Avogadro's number, and we end up with 5.54 times 10 to the 22nd atoms, which is a lot. We would expect this number to be quite large when we're doing kind of analysis of our answer here. We'd expect it to be big because we're talking about a number of atoms. And we would expect it to have 3 significant figures because we're limited here. When we're talking about Avogadro's number, this is kind of a count or a definition. So the 6.02 times 10 to the 23rd is not something that you have to take into account for significant figures. This would be an exact number. Your mass, though, is going to be inexact because it's a weighted average, and the measurement itself, of course, is inexact. So we're limited to the 3 significant figures in our answer. We're expecting it to be large, so that kind of jives. All right. So if you have any questions on this, don't hesitate to reach out, and we will get into some more detail about how we can use this information to go from moles or grams of one thing into moles of grams or another when we talk in future videos about stoichiometry.